Dear students, today we will discuss about voltage divider biasing and what is the condition to provide the best bias stability in this circuit. First thing, it is a divider biasing. Why it is said to be a divider biasing? Because of this divided network. This is a voltage divider network which is consisting of two resistor R1 and R2. So you can see here. So this is your VCC and R1, R2. Because of this arrangement only we are saying it's a voltage divider network consists of two resistors R1 and R2 between the supply voltage and the ground. So R1 R2 is a divided network. Because of this only the name came voltage divider network. And the very important thing is the drop across this resistance can be varied. That is very important. So that is a novelty part in the divider network. Another thing, the voltage at the midpoint of the divider is used as a bias voltage for the base terminal. That means the base emitter junction is followed by the voltage drop across the lower resistor R2. Another thing, the drop across the resistance can be varied. That is very important. That is a flexible part in the divider network. The drop across the voltage can be varied by changing the resistance. Another thing, the voltage at the midpoint of the divider act as a bias voltage for the base terminal. Very important. Repeating, the voltage at the midpoint of the divider is used as the bias voltage for the base terminal. So this is a base and this is a emitter and this is a collector. Right. Another important thing is the drop across this R2 only will forward bias the base emitter junction. This RE, it is acting as a feedback network. It is indirectly affecting your input. How? We know that VBE equal to VB minus VE. If there is a change in the voltage, we'll consider scenario also. If there is a change in the VE, so what happened generally? So when V E is increasing, obviously VB will reduce. When VB will reduce, IB will reduce. So when IB is reduced, IC will reduce. So the changes is compensated. The increase in the changes will be compensated. For example, consider the scenario. Due to the changes in your supply or changes in the transistor parameters, there is a change in your IC current. Okay, there is a change in the IC current. Okay, there is a change in the IC current. So we know that same IE also will reflect. IE also will increase because IC is approximately equal to IE. That means the voltage drop across your VE will be increased, right? So what is the condition? VBE equal to VB minus VE. So when V is increasing, obviously VB will decrease. When VB is decrease, what happen? Your IB will decrease. When IB is decrease, your IC will try to compensate. Whatever the change that is compensated because of this RE network. So the RE network will act as a feedback to adjust the input voltage. Based on the adjustment of this input voltage, the IB will tend to reduce. Once IB is reduced, your IC also will reduce. So this is the way how the divider bias network is working. So RE is a feedback resistor. Okay, now we want to find what are the current terms IBQ, ICQ. Okay, so I am going to simplify this circuit. Okay, I am going to redraw this circuit as the Thevenin equivalent circuit. I am going to redraw as the Thevenin equivalent circuit. I am going to redraw this circuit as a Thevenin equivalent circuit. So first step is I'm removing this VCC. I'm separating. So if you separate, what you'll get? So here you have a VCC and here you have a VCC. Then this is your R1, R2, then this is your RE and this is your RC. Okay, so when you are doing the DC analysis, we know that capacitor will become open circuit and Vs will become 0. So no need to consider this part. So now what I have done, I have separated this VCC. Okay, and I can draw like this, right? See, I can draw like this. So this VCC and plus minus, where this is a plus, right? So minus will be in the down part. Understand now? So this is a plus actually. Minus is grounded. So that's what we have done. Then following this plus, you have a resistance, right? So I have resistance R1, then R2. So that is connected to the base emitter collector. So RE RC plus VC. See, this is a redrawn circuit. Okay, now I'm going to consider. See, what is the need of what are the things to be found in the Thevenin equivalent circuit. You want VTH, then you want to find RTH, then you want to find the load. This is a load, right? So this whole part is load. This whole part is load. This whole part is load. Now we are going to find VTH and RTH. First we will find RTH. When you are finding RTH, what do you need to do? So you need to short circuit the voltage source. So R1 R2 will become parallel. So RTH equal to R1 parallel to R2. Right. Then we want to find a VTH. This is very important. To find a VTH, that means I want to find what is the drop across this R2, because this is a load, this is a load, this is a simplified circuit what you explained in the last slide. So I want to find what is the drop across this. So this is nothing but your VTH. So we will find, that is corresponding resistance divided by sum of the total resistance into source voltage. So that means VTH equal to VCC corresponding resistance R2 divided by R1 plus R2. So that is we calculate VTH drop across R2, that is VB, that is a drop with respect to base terminal, and nothing but a VCC into R2 divided by R1 plus R2. Okay, so now we have got VTH and RTH. Now we can go for the simplified circuit. So now we can see VTH, RTH. So these are simplified Thevenin equivalent circuit. Here you can see VTH, RTH, and this is your load. This complete part is a load. So now you can find your IBQ, your ICQ, and VCQ, right? So this is a Thevenin equivalent circuit. How I am saying the Thevenin equivalent circuit? So Thevenin equivalent circuit, you know that you have one VTH, one voltage source, one series resistance along with your own load. So same logic, you redrawn our circuit in terms of Thevenin's model. Now we want to find what is our IB, ICQ and other terms. Okay, so first you consider, first we will find what is our emitter current. So I will draw like this. So this is your IB current, this is your IC current, and this is your IE current. See, for this node, this is entering, this is entering, this is outside. That means IE equal to IB plus IC. So that's what I written here. That is your outgoing current with respect to this I have written equal to sum of the incoming current parameters. So we got this one. IE equal to IB plus beta times of IB. This is a powerful relation, we know that. So IE equal to IB I have taken outside. So IE equal to IB into 1 plus beta. This we will use for our solving this equation. Okay, that is IE equal to IB into 1 plus beta. Now we want to apply the KVL in the Thevenin equivalent circuit. Very simple. See, first this is the input load, right? This is the input load. This is the input load. Now I am going to apply the KVL in this direction. Now minus to plus, entering at a minus, leaving at a plus. What will you get? Plus DH. Entering at a plus, leaving at a minus. This you need to assume. You can take either entering symbol, current symbol, or exiting symbol. I am taking the leaving current symbol. So what will you get? IB into RTH. This is voltage, right? So in terms of product of current and resistance, I am writing minus this junction voltage. What is the junction voltage? VB, because this is PN. So P is positive, N is negative. So that's a P defined by positive and N defined by negative term. So this is always fixed term. This is a fixed one. So entering at a plus, you can see this is entering at a plus, leaving at a minus. So minus VB. So now it is entering at a plus, leaving at a minus for this RE resistor. So what you get? Minus IE RE equal to 0. So what I am doing, I am taking this minus term all to the right side. So this equation will become like this, right? I am bringing this minus term to the right side. So VTH equal to IB RTH plus VBE plus IE RE. So what is IE? We know IE is nothing but IB into 1 plus beta. So this one I have substituted. So here I am taking IB outside. So here you can see here IB coefficients are there. From here and here I am taking IB outside. So RTH plus 1 plus beta RE. So now I want to find what is IB. So you bring this VB to the left side. So VTH minus VB divided by RTH plus 1 plus beta times of RE. So this is your IB equation. So what is the relation? We know I is equal to beta times of IB. So just multiply beta with IB. So you will get beta into VTH minus VB divided by RB plus 1 plus beta RE. That's it. Okay, now we are going to find what is your output side, right? See, this is a loop actually. So if you are beginner, so you may have a doubt. See, what I will do is a loop. So this loop I will put separately. So first this is a plus, right? So plus minus the downside. So following that, what you have? Plus minus. That is RC. I am just considering plus and minus. That means this resistance will be plus and minus. It is an assumption, right? The first passive element I am taking plus minus. Then this is a fixed polarity. So plus minus, that is VC. Then this resistance will be plus minus. So close it. So plus minus. Now you apply the KVL. Same. Now apply KVL. This and this both are same. See, when you are the beginner, you can try like this, right? So what is this? VCC. And what is this? IC, RC. Then this is your IER. That's all. Now become very simple, right? See here, my entering at a minus, leaving at a plus. So plus VCC plus VCC. Entering at a plus, entering at a plus, leaving at a minus. So minus ICRC. Entering at a plus, leaving at a minus. So minus VC entering at a plus, leaving at a minus. So minus IRE equal to 0. We know that I is approximately equal to IC. With that relation, so what I am going to do is, this from this equation I am taking this all minus term to the right side. So what happened? So I am taking VC to the left side, I am taking all terms to the right side. So it becomes, so minus will become plus, right? So this will become plus VCC minus ICRC minus IR. So this is the equation you have written here. Now we know the relation IC equal to IB. So with that relation I can find VCC and IC you take outside. So RC plus RE. That's all. Now see, with this equation I can find your maximum IC current and maximum BC voltage, and you can find the load line. Then you can find your ICQ current, then VCQ current, VCQ voltage, that is the operating voltage VCQ and operating current ICQ. So that we will discuss in the problem. Okay, so this is a master equation. Okay, this is a master equation. From this we can find load line, then we can find the quotient point from ICQ current equation and VCQ voltage equation. Now another thing, so loading effect. What is a loading effect? Loading effect generally reduces the voltage level of the voltage source. See, suppose I am giving 5 voltage as a AC source. When it come to the, I am giving AC source 5 voltage. When it come to the base terminal, your voltage will reduce. For example, if I am giving 5, when it come to the base voltage, you will get only 1 if you have a higher loading effect. When you have a less loading effect, you will be getting 4.3. So this is a very important when you are designing divider biasing circuit. It is a must to reduce the loading effect. It is need to minimize. What is the condition to minimize? So condition to minimize is, we need to consider this resistance. What is the resistance? We know that this resistance IE equal to IE plus IB plus IC. So IB plus beta times of IB. So this is nothing but a 1 plus IB into RE. So what is the resistance across this circuit? That is 1 plus beta times of RE. That is the resistance, right? So that's what the written. 1 plus beta RE should be greater than RTH. That means 1 plus beta RE should be more greater than RTH. If you maintain this condition, loading effect can be minimized. And also see, if I consider what is a IC equation? So we know that DTH minus VBE divided by RTH plus 1 plus beta RE. This is the equation we studied, right? So with this consideration, I can write IC equal to beta VTH VBE divided by 1 plus beta RE. Okay, so here I can take beta divided by 1 plus beta, I can take it as 1, approximately 1. So like 100 divided by 101, approximately 0.99. I can take it as a 1. So with that, I am taking whole factor as a 1, and you can see the updated equation. So IC equal to VTH minus VB on by RE. So you can see this ICQ is independent to the changes of beta. If beta whatever change, ICQ will not change. That is the best thing in your voltage divider biasing circuit. the voltage divider biasing circuit, your IC is independent to the beta variation. That's the first thing you have to remember. The second thing, to minimize the loading effect, I need to maintain your RTH. RTH should be approximately zero point 0.1 times of 1 plus beta RE. That means your RTH should be less than 1 plus beta times of RE. That means what you is understanding? This is RA. RA is this resistance. This RA should be greater than RTH. So even I can say like RA should be greater than 10 times of your RTH. So see, I can write like this. If you bring this point on this side, what happened? 10 times of RTH should be the 1 plus beta times of RE. That means this is what RA, right? So that means your RA should be equal to 10 times of RTH. If you follow this condition, I can reduce the loading effect. I can minimize the loading effect in the circuit. Okay, this is a bias stability condition you have to follow when you are designing the divider biasing circuit.